All right, let's dive right in. Today, we are going on a hunt for a particle that, according to some of our best theories, absolutely has to exist, even though nobody has ever seen one. We're talking about the magnetic monopole, a north pole all by itself without a south.
So let's start with a question you've probably asked yourself at some point. You've got a regular bar magnet, you know it has a north and a south pole, so why can't you just snap it in the middle and get a separate north piece and a separate south piece?
You know how this goes, right? It's one of the first things we learn about magnets. You take one, you break it, and bam! You don't get two halves, you get two brand new, smaller magnets, each with its very own north and south pole. Do it again, you get four. Keep going down and down all the way to a single atom, and you still have a tiny little magnet with two poles. You never, ever get a lone north or a lone south. Now, don't worry about the crazy math here. Just look at the pattern. On the left, you've got Maxwell's equations, the rules of the game for electricity and magnetism. See that top equation for electricity? It has the term for electric charges, like electrons. But look at the one for magnetism right below it. It just has a big fat zero. That zero is the rule that says no magnetic charge is allowed. And to a physicist, that just looks wrong. It's lopsided. Their dream is on the right, a universe where magnetism has its own charge, its own monopole, making the equations perfectly balanced, perfectly symmetrical. Just beautiful. But this wasn't just about making things look pretty on a page. That del dot B equals zero was considered a fundamental law of physics. It described the world we actually see. And what it says, clear as day, is that magnetic monopoles are forbidden. Magnetic field lines can't just start or stop somewhere. They have to loop back on themselves. Case closed. Or so everyone thought. And then things got even more complicated with the rise of quantum mechanics. It introduced this deeper, weirder idea called the vector potential. You can kind of think of it as the field behind the magnetic field. And here's the wild part. Experiments showed this thing was real. Quantum particles could feel its effects even when the magnetic field itself was zero. This wasn't just some mathematical party trick. It was a fundamental piece of reality. So here was the argument, and it seemed totally airtight. Quantum mechanics, our most successful theory ever, needs this vector potential thing to work. And, as a matter of pure math, if you have a vector potential, you simply cannot have a magnetic monopole. It looked like checkmate. The beautiful, symmetrical dream was just a dream. But then, this guy comes along, Paul Dirac. In 1931, he writes this paper where he casually predicts the existence of antimatter in the first couple of paragraphs, and then he basically says, yeah, that's neat, but that's not what I'm really excited about. Let's talk about magnetic monopoles. For Dirac, the real prize, the most beautiful idea, was the monopole. And Dirac, he found an astonishing loophole. He realized that the very same quantum weirdness that made the vector potential seem so rigid and necessary also made it a little bit fuzzy, a little bit ambiguous. And right there, in that mathematical ambiguity, he found a secret door. The very thing that seemed to forbid monopoles was actually the only way they could sneak into existence. And this is his incredible conclusion, all boiled down into one simple, elegant equation. What Dirac showed was that if even one single magnetic monopole exists with a magnetic charge G, then its existence must be tied to the electric charge Q of every electron and proton in the universe. They're not separate things. They're locked together by quantum mechanics. Okay, so it's a really neat equation. But why is this such a big deal? Why does this one little formula totally change the game? Because of this, for as long as we've known about them, we've wondered why electric charge comes in these perfect little brackets. Why is the charge of a proton exactly the opposite of an electron's? Why not like 1.00001 times? Nobody knew. Dirac's equation gave us the answer. If a single magnetic monopole exists anywhere in the cosmos, it forces all electric charge everywhere to be a perfect multiple of some basic unit. It solves one of the deepest mysteries about why our universe is the way it is. So, just like that, Dirac flipped the whole story. The monopole went from being impossible to being almost essential. But the story gets even stranger because it turns out we're not just looking for one kind of monopole anymore. Now there are two. To get your head around this, think of it like a magic trick. You think I have one thumb here, right? A single magnetic dipole. And look, I can pretend to pull the North Pole right off. But of course, the trick is that I had another thumb hidden the whole time. By arranging lots of north-south pairs in a clever way, you can create the illusion of a single separated pole. And that's the key to what we now call an emergent particle.
So this gives us two totally different kinds of monopoles to hunt for. On one side, you have the fundamental kind, the real deal that Dirac predicted, a true elementary particle, a leftover from the Big Bang, that could just be flying through empty space. That's what they're looking for at places like CERN. And on the other side, you have these emergent monopoles. They're not real particles, they're more like a collective illusion created by zillions of atoms inside a crystal. They can only exist inside that material.
And here's the modern twist that takes us from impossible to, well, inevitable. Our current recipe for the universe, the standard model, it works great, but it doesn't need monopoles. But almost every single theory that tries to go beyond it, grand unified theory, string theory, you name it, they don't just allow for monopoles, they demand them. The existence of fundamental monopoles is pretty much the only thing all these competing next-level theories agree on. So, if our best guesses about the future of physics all say they must exist, where are they? Well, this has kicked off a global manhunt. But how do you even look for something like this? It turns out you need two completely different strategies. At CERN, where they're hunting for the fundamental kind, they're looking for a signal that would be impossible to miss. Theory says that if they create a monopole, it would blaze through their detectors, leaving a trail of energy 4,700 times stronger than a proton. It wouldn't be a needle in a haystack, it would be a freight train. And the result of their search so far? Absolutely nothing.
Okay, but what about the other kind, the emergent ones inside a crystal? The search there is way more subtle. You can't just smash things together and look for a big flash. For these, you don't look for them. You have to listen for them.
It's an amazing experiment. Scientists take this special crystal called a spin ice and cool it down to just a fraction of a degree above absolute zero. In that state, the magnetic atoms inside can arrange themselves so these emergent north and south poles can pop into existence and wander around. And using a super-sensitive detector, they listened to the magnetic noise inside the crystal. And you know what they heard? They found the exact, unique, pinky red sound profile that the theory predicted. It was literally the sound of magnetic monopoles moving around. So where does that leave us? We found one type of monopole in the lab, but the fundamental one is still missing in action. And this whole incredible story leads to one last mind-bending question. What if our entire understanding of physics is just one of two ways to look at the universe? This is a wild idea called electromagnetic duality. It suggests there could be two completely different but equally correct instruction manuals for our universe. In our manual, we start with electric charges, with electrons, and magnetism is this complicated thing that comes along for the ride. But in the other manual, you could start with magnetic monopoles as the fundamental particles, and electrons would be the complicated things that emerge. They're just two different ways of describing the exact same reality, and it suggests that the monopole isn't just some missing particle, but a key to a much deeper, hidden symmetry of the universe itself.